Yes, class. Am I audible? Good evening.
Good evening, ma'am.
Who all are present right now? Anushka, Laya, Liana, Rayan, and Rizan. So in the last class, we had seen certain cases. These questions basically we had seen if all of these are combined together. Semicircular wire, circular loop, all these if are combined together, then how will we solve the questions? So for semicircular wire, we had a formula. For infinitely long wire, we had another formula. For semicircular wire, for a semi-infinite wire, for at the center of a circular arc, we had the formula. Then we also had the formula for a random circular arc, means which is subtending a random angle at the center. So for example, in this question we had seen it was subtending pi by 3. Now, one last case in this is left that we didn't discuss in the last class was, see, circular loop is if a circular loop is present. If a circular loop is present, what happens? At the center of the circular loop, we have calculated that was mu naught I divided by 2r. What if at this axis, if this is a circle, then there will be axis of along the center, axis of the circle. Then at this axis, if I want to find out what's the magnetic field, there will be a different formula, because the formula that we have calculated, that is for the center of a circle. This time we are not focusing on the center of a circle. This time we are focusing on the axis of the circle. So axis of a circle has a derivation that we'll do, and that's not the exact derivation. Remember here the derivation for the circular one, I was just using one content, and here only I was rubbing it and I was writing it for circular, semicircle. This time derivation for the axis one is different. So that let's start. Magnetic field on the axis of circular coil. So axis of circular coil means, see, see, if I have made the circle like this, it means the circle is kept in YZ plane. YZ plane means, for example, this is your XY plane. I think I have discussed XY and YZ plane and ZX plane in the last class as well. So this is what? This is X axis, this is Y axis. Anything kept like this in your plane, that becomes what? That becomes XY plane. If anything is kept like this, if I show this like this, it will be a straight line that will be visible to you. So this is Y axis, this is Z axis. Similarly, the circle, instead of keeping it like this, we are keeping it here. And now the axis, this is the axis of it. From here at this axis, we'll be having a certain point. Fine, from this point, if I ask you, at the center of this, we have calculated mu naught I divided by 2r. Now at the axis, here somewhere we are trying to find it. So that's why I have drawn this like this. Firstly, understand this is a circle only, it's not an oval or a different figure. Fine. So this is a circle with radius r. It's a circle with radius r. Now see, this is the axis of the circle which I was referring. Now at this axis, if I want to find out the magnetic field, then what will be the magnitude of the magnetic field? Now see, let's say this is x, and this is the radius of the circle, which is capital R. So this is the axis x. At this point, at this axis, along this axis, we are trying to find out the magnetic field. Now, if I take a small element dl we have been taking. dl is what? What's the name of dl that we had assigned it?
Current element.
Current element. So from two diametrically opposite ends, I have taken two dls, means two current elements. Current element is actually what? It's just a cross section or just a cut from the whole wire. If a whole wire is having certain values, let's say this is a complete wire, then from a wire we have cut a very small section element. That is dl over here. So from two diametrically opposite ends, we have taken dl. So how did I choose this dl? This is from two diametrically opposite ends. It means if this is your circle, for example, from here, if I have chosen dl, this becomes two diametrically opposite end. Reason for choosing these two diametrically opposite is the fact that when you choose these two, then that is valid for all the diametrically opposite ends. And ultimately what will happen? When you will combine all the diametrically opposite ends, that will form you the complete circle. All right, so for that complete circle, we have chosen this. Now at this point, let's say this is some point P. So for Biot-Savart's law, we always use the separation between current element and the point. That is known as the radius vector. No, this is the axis. This we cannot consider in our Biot-Savart's law. What can we consider? What do we consider? That r square that comes in the formula of Biot-Savart's law. What is that? That is actually the radius vector square. Here the radius vector will be what? Position that point P from where you want to calculate the magnetic field to the current element. That is your separation. So DL is this current element. This is your point P. So can anyone tell me what should be the value of this? From here, what should be the value of this? Look, this is a right angle triangle. Here, this is forming a right angle triangle. This value. Yes, class? R square plus x square, no, under root will also come, no? If you apply Pythagoras theorem, so that will be hypotenuse square as well. So yes, and under root will also come. This will be capital R square plus x square. Let's, for the meanwhile, for the ease of our calculation, let's write it as small r. Because if you write it as small r, then at the end we can substitute the values of small r. Right now, let's focus on it. Now, regarding the magnetic field, here we have to perform certain calculations. This is what? This is your magnetic field. Just a second. See, from here, this DL will be executing certain magnetic field. So let's say the magnetic field is over here. This is a straight line only because I have drawn it with two colored bits. That's why breakage is visible. So at this point, because of the circular element, magnetic field is pointing like this. Let's say this is dB. Why dB? Why not B? Because we have chosen DL. DL is a very small current element. So dB becomes what? dB becomes the magnetic field because of that current element. Similarly, from here also, you will be having a value of dB as well. From here, what will happen? dB, that is the magnetic field, will come. Now, we have to perform resolution of the vectors. Resolving the vectors along x and y plane, because these are lying in xy plane, and xy plane you must have studied in your class 11. You cannot use it directly. You have to resolve the vectors first. So for resolution also, let's say this angle is theta, or let's choose this angle as theta. If this angle becomes theta, this is 90 degree. This will be 90 degree minus theta. Right, I will show you why this angle is theta. Let's say the angle between the position vector and the radius, this is theta. This is 90 degree, so this will become 90 minus theta. This whole was 90, so this again become theta. And this becomes again 90 minus theta, so this is theta, this way. You don't even need to remember, and you don't even need to mention in the derivation why you are choosing that theta. In the exam, directly say that angle is theta, so this angle is directly theta. No need to even mention it why this is 90 minus theta. That is just for your knowledge, for your clarification of your confusion. Now, resolution of vectors. Now you have to resolve these vectors. This is theta, so definitely this will also be theta. Now we have to perform resolution of vectors. See, this angle is theta. So along this axis, we will be getting component dB cos theta. The axis with which the angle is made, that is chosen as cosine value. So this will be cos theta, and the perpendicular one, this becomes dB sine theta. Fine. Now the other component that is coming here, this dB. This is also making angle theta with the x-axis. So what will happen over here? If you resolve this, this will again be dv cos theta. And the perpendicular one to this becomes db sine theta. This is the resolution of vectors of magnetic field dB at this point P. Now this is due to just two components dl, which are at diametrically opposite ends. Now you have to see what will happen. This whole resolution will occur for all the diametrically opposite ends. For example, see, this is a circle. If I choose 2 points from here, fine, from here if I choose 2 points, so whatever will be the answer, whatever will be the solution because of these, similar will happen for these also, for these also, for all the diametrically opposite ends. Just focus on this y-axis. Y-axis is having db sine theta above, db sine theta below. It means db sine theta will cancel each other. So all the db sine theta that are present because of all the diametrically opposite end, that will cancel each other. And what happens to cos theta? All the cos theta, see, this was your circle, all the cos theta are pointing here. All the cos thetas are pointing towards the right side. In the figure, it's right side. So from the front view, you can say all the cos theta are pointing upwards. All the sine thetas are getting cancelled. Cos theta will get added up. You can see in the figure as well. db cos theta, when it got resolved, both got added. Whereas sine theta, it was in opposite direction. So that will get subtracted. So what I'm trying to tell you is the fact that sine theta, db sine theta, which is getting cancelled for these two, will be for all of the diametrically opposite dls. Means that will cover and make your circle complete. Fine, class. Now we can perform the calculations. dv sine theta has been, so see, let's say magnetic field across y-axis will be what? Magnetic field at A due to L. At the point due to L, we are trying to find out. So Biot-Savart's law is what? Mu naught I dl sine theta divided by 4 pi small r square. Small r is the separation between dl and the point P I have taken. Now magnetic field applied across the y-axis. See, magnetic field applied across the y-axis will be what? All these db sine theta, it will be subtracted because both are in the opposite direction. They get cancelled. There is no net magnetic field across the y-axis. Clear till here? First tell me, is this point clear? Then we'll move on to x because x has calculations. Clear?
Ma'am, can you explain that again?
Yes. Imad, say.
Can you just explain that again? Just y-axis again.
See. This is the figure. When we resolve the vector magnetic field, one resolution is clear to you, no? How we have resolved this. Now see, db sine theta is pointing upwards. Let's say positive y-axis, that is j cap. Other b sine theta is pointing downwards, that is negative y-axis or minus j cap. So both will cancel each other. What will happen? For these two dl, they have cancelled each other. If you take another 2 dl, these two diametrically opposite, that will also be 0. So net magnetic field across y-axis, what are we getting? That is 0. Clear?
Okay.
Somebody else was asking something. Anushka, were you asking something?
No, ma'am. I was saying that it's clear.
Okay. Now let's do the calculation part for db cos theta, because x-axis, we have it along x-axis. So along x-axis, what will happen? That won't be 0. It is getting added up. So db cos theta from two diametrically opposite end, then db cos theta. Likewise, all the db cos theta that are present for the complete full circle. Fine. Now see, X is what? Px is the magnetic field that is along the x-axis. And along the x-axis only we are having the component what? We are having the component dB cos theta. So we can directly say it is integral of dB cos theta. Fine. This is dB cos theta. Now dB is what? What is the value of dB? dB's value from here above you can say mu naught I dl sin theta. There is no need to put theta because you can directly see. dl is again for every circular part we have seen that dl will be tangential and radius will be pointing towards the center, so that will make 90 degree. So that is the same the way we have done it previously as well, so that will be the same. So mu naught I dl sin 90 is 1 4 pi small r square. This is dB. Before we substitute, let's write the value of cos theta as well. This is a little lengthy, but if you remember, y-axis will be 0, x-axis find dB, and cos theta substituted, you will get the answer. Because this comes in exam to derive this. Now cos theta. Look at this. This is, let's say, point P. This is A. This is B. If you look at this triangle PAB, what is the value of cos theta? See, this is theta. So this becomes the base, right? And this is the hypotenuse and this is the perpendicular. So cos theta is what? So we have to find out cos theta. So in triangle PAB, this only right angle triangle we are focusing on, this right angle triangle we are obtaining. So here we want to find out the value of cos theta, that is base divided by hypotenuse. Now base will be what? If you look at this triangle PAB, base is AB, that is capital R. Hypotenuse is PA, which is small r. So that becomes capital R divided by small r. This is the value of cos theta. Capital R divided by small r. Now your dB is also ready and your cos theta is also ready. You just have to put it in the values. So Bx will be what? dB is mu naught I dl. This is 4 pi r square. And instead of cos theta, you have capital R divided by small r, right? And we are integrating it, obviously. So bring all the constant terms aside. Mu naught I dl, not dl. dl is not a constant term. We have to integrate dl. So mu naught I capital R divided by 4 pi small r cube. This is integration of dl. Now again dl, if you will add all the dl's, what you will get? If you integrate all the dl. If you integrate all the dl's value, that is combining your whole circle. dl is pointing.
L, ma'am.
Yes, L. L, that is the length of the circle. So what's the length of a circle? 2 pi r. Right, you are integrating it completely. So put in the value mu naught I r 2 pi r divided by 4 pi small r cube. So pi gets cancelled, 2 gets cancelled. What are we left with? We are left with mu naught r square divided by 2 r cube. This is the formula of magnetic field. Fine, class. Before just we end this, one last thing. Net magnetic field will be what? By plus bx. By is already 0. So total magnetic field will be this only. So net magnetic field will be mu naught I capital R square divided by 2. Now put the value of small r. Small r was what? Under root x square plus capital R square. Remember that hypotenuse we were obtaining. So this becomes r square plus x square to the power 3 by 2. 3 already from here and half from the root. Fine, class. So note it till here. Then we'll solve certain questions based on this. So at whatever step you're not able to understand, ask me. Start from here. And in the exam, you have to draw this figure where you are mentioning all the forces and all the magnetic field that are acting.
Mom, could you scroll up? Just 2 minutes.
Ma'am,
Yes, Anushka.
ma'am, is this derivation important from board exam
Yes,
perspective?
yes. From board exam, this is important.
Yes, ma'am.
Usually, numericals do not come from this because the formula you can see it's a long formula, no, with the powers of 3 by 2. So maximum, if any question has to come from this portion, usually it's the derivation that comes. Numericals are usually not given from this. That's why I'm saying focus on the derivation.
Yes, ma'am.
Done.
Yes, ma'am.
Yes,
Done.
ma'am.
Written now.
Let's just see one numerical also. I think there will be like this. If the numerical comes from here, more or less the values are usually not given. Like in your electric field portion, you have electric field at the equatorial line, at the axial line. There you make an approximation by which you get the formula 2 kp divided by r cube. Otherwise, the formula is not 2 kp divided by r cube. It's under root r square minus a square, like this. So that's why usually the formulas are, or even if the numerical will be given to you, it will be in such a manner that you will be able to solve with all the power of 3. Like 8 will be given. So you can even, or 4 will be given. Like these values will be given, which you will be able to do. So see, this says what? You have to find the magnetic field at O. This point you have to find the magnetic. This is one, this is second. So this is kept in YZ plane. This is kept in YZ plane like this, and the other one is kept like this. Fine, this is the way how it has been kept. So this is a circle whose radius is b. This is another circle in xy plane whose radius is small a. Both have the separation of their axes to the point of calculation as x only. And current is also same. Current is I, that is one. Now see here, I'll leave the answer in terms of I cap and j cap, because in this question you can. Net magnetic field will be what? Net magnetic field will be sum of magnetic field due to the first one and the second one. Now, B1 will be what? See, when you will be writing these questions of magnetics in your exam, remember one thing. Suppose this is a question. Right now, I am not solving it in that manner. You have to do what? You will write net magnetic field is due to B1 plus B2 plus B3 plus B4, whatever segments are given to you. Then you will say B1 is this, B2 is this, B3 is this, and then you will write it. Then B1 plus B2's magnitude, and then whatever is your answer. I am doing it in one line. B net is B1 plus B2. So I'll write down the values of B1 here only and B2 here. You in the exam write it separately. B1 is this along with its direction. For example, mu naught I something k cap like this. Then write, leave some space, write B2 is this, B3 is this, whatever is there. Fine, like that. Try to mention that if you are having time. If your deficit of time paper is nothing, then write it in a single line. Now B1 will be what? See, mu naught, current is I, radius will be b square divided by 2. Now you have b square plus separation of the axis is x square to the power 3 by 2. Fine. Now we'll apply our right hand thumb rule. For direction, right hand thumb rule is fixed. Here what will happen? This is an xy plane. Like this it is kept. So current is flowing like this. If you look, if you whatever you have, you must be having a mobile phone, something else you'll be having, so that you can imagine. If anybody is having difficulty in imagining this, then see from your side you will see what? From your side you will see current is entering. Current is moving into the page. See in the figure, you will be able to see this. Current is moving into the page. And from below the current is coming outwards. Same thing here will happen. If current is moving into the page, current is moving into the page. So I'll curl my fingers like this. Thumb is pointing towards where? Thumb is pointing towards the right hand side. So this becomes minus I cap. Fine class, right hand. For this second one, see, it is kept like this. And current is from the inward, it is going like this. And from the side that is facing me, current is moving like this. So this is the flow of current like this. So I'll curl my fingers same way. Thumb is pointing upwards. That is J cap for the second one. But first let me write down the magnitude. Mu naught I a square by 2 a square plus x square to the power 3 by 2, and this is J cap. This much of Tesla is the magnetic field. Fine, noted down. Any doubts, then ask me. Then we'll start with Ampere Circuital Law.
Ma'am, I means along x-axis, right?
Negative x-axis minus I cap. I is the universal unit vector for x-axis.
All right, ma'am.
Direction of the second ring. See, second ring is kept like this. This is the second ring. So current is flowing. If you look it from your side, current is moving towards the right, and then from the backward it is moving towards the left. So initially towards the right, and then it is moving towards the left. So towards the right, then towards the left. This is pointing upwards. Got it, Liana?
Yes, ma'am. Thank you.
Just note it down. Then let's take a break of 5 minutes. Exactly after 5 minutes, I'll start with Ampere Circuital Law. All of you are here. Let's start with then Ampere Circuit. Now see Ampere Circuital Law. So Ampere Circuital Law will be slightly similar to Gauss theorem. Gauss law you all remember? You must have studied Gauss theorem. Can anyone tell me what was Gauss theorem? Not the exact statement, at least somewhat. And I'll connect it. Anyone? It was related to electric field. This much you people remember?
Yes, ma'am.
And was Gauss theorem the net electric flux?
Yes, yes. Net electric flux. Good. So net electric flux was equal to what? See, flux is equal to Q by epsilon. Exactly. So electric flux, let's just quickly revise electric flux because this topic we all have not done it together. So electric flux is basically electric field dot the surface area, E dot ds. This flux is equal to charge enclosed divided by epsilon. That is your Gauss theorem. I hope now you are able to recall. This was your Gauss theorem. Fine. Now Ampere Circuital Law, please try to relate it with this. Let's say a wire is there. Fine, a wire is there. I'll send you the video lecture of Gauss theorem which we did in this batch. So all those who have missed, I think all of you are new students only from here. So that I'll send you just whenever you get free time, not compulsorily before tomorrow, whenever you have time. You can even forward it and skip it. For at least the major part you can see and the question at least. Because Gauss theorem is very important and it will be a revision for your half yearlies also. So if you have a wire, fine, and it is having current I. Now, the line integral means P dot dl. This is meant by line integral. So line integral, the way there was E dot ds, here we have B dot dl. This is equal to what? Let's say this is along a closed loop. This is equal to whatever is the total current enclosed. There in case of Gauss theorem, in case of electric charges and field, we had charge enclosed. This time we'll be having whatever is the total current enclosed. This is equal to the total current enclosed. And instead of 1 by over epsilon naught, here we had 1 over 4 pi epsilon naught. Here we'll be having just mu naught. So B dot dl is equal to mu naught I. And this term we call it as the line integral. You are integrating it along the whole line. That is known as line integral. So B dot dl is equal to mu naught I. This is your basic Ampere Circuital Law. If you remember this much, your full marks will be given whenever Ampere's law statement is asked, because certain laws are there whose statements are asked. Gauss theorems, what is the statement of Gauss law, Ampere Circuital Law, all these. And if it's a long answer question, then one of the derivations are included with it. For example, it can be asked, using this Gauss theorem, derive the expression for the electric field of an infinitely plane sheet. Like these questions are then continued. But if it's just for a 1 or 2 marker, then the exact law statements are asked. So I think I have written it for you. See, according to Ampere Circuital Law, line integral of magnetic field means B dot dl along a closed loop is mu naught times the total current enclosed by the loop. Means B dot dl is equal to mu naught I. Using this, we'll be figuring out what's the formulas for, applications for Ampere Circuital Law include solenoid and toroid, and those are simple. So this is not a tough portion. Fine. Ampere Circuital Law is not tough. In fact, I will say Gauss theorem is tougher than this because there are applications, the applications are numerous. For even spheres are there. Fine. So here we are just focusing on line integral of magnetic. So according to Ampere Circuit Law, this is what Ampere Circuit Law is. There are certain steps, there are certain conditions that let's discuss those conditions. But again, I'm saying, I'll send you the video lecture today on WhatsApp. Do check that video. Wherever you're having doubts, ask me. So B dot DL, if you have a closed loop means if I have chosen this section, then even if the total current across this whole wire is I, but if let's say I want to enclose this area. So anyways, I will have to find the current enclosed in this area. Just focus on this I enclosed. If you have suppose some area, here current is entering and here current is leaving, then current is entering, and so I enclosed will be, and some current is outside also, leaving and entering. You will just consider these which are present over here. You will just consider these. So plus I minus I, that will give you plus I. You will not consider these. So within the closed loop. Now Amperian loop, Gaussian loop we used to take in case of Gauss theorem. Gaussian pillbox, Gaussian surface was there. Amperian loop is just closed loop. There are not so much conditions for Ampere circuit. Amperian loop is what kind of loop? It should be closed. This is the first condition. Even if it is an open loop, if it is an open loop, you will make it close, or you will not apply Ampere circuit law. By other means, you'll answer the question if your Amperian loop is not closed. So choosing Amperian loop is in your hand. Just choose the Amperian loop directly. So it should be closed. Fine. Second point, it should be either tangentially or perpendicular to the loop. Should be either tangential. Yes, Aya.
Thank you, ma'am.
So it should be either tangential or perpendicular. Now, why are we focusing on this fact, whether it's tangential or perpendicular? This is because of the fact, see, when you have a circle, if we choose a closed Amperian loop, usually it's in the form of circle. So when you choose the element DL, current element DL lies where? I have told you, and today's class also, we have seen it so many times, that DL is tangential. So to make that DL tangential, we choose our Amperian loop as circle. Fine. And it's one of the conditions. Now, magnetic field should be constant or uniform. This is very important. The other points, first, the very important point is it should be closed. Second is tangential point is not so important. This point is very important, that magnetic field has to be uniform or constant. Now, what's the reason for this? The reason for this is that you are integrating. P dot dl, you are integrating. So if your dl is variable, you will integrate it. For example, dl in all the cases that we had studied last week, it was variable. We had to somewhere write 2 pi r, somewhere we wrote pi r like this. Fine. If your magnetic field is also variable, then it will be a cumbersome process. So if your magnetic field is constant, how do we do integration? We put the constant out of the term, out of the integral line. So if your magnetic field is constant, you can write magnetic field and then you can integrate. That's why we choose Amperian loop like this. Now, there are certain steps for the performing of this Amperian circuital law. So we'll be doing that with the help of cylindrical wire, and that cylindrical wire is included in your course as well. So with that help of example, you will be able to firstly understand what is the formula for cylindrical wire. Secondly, you'll be able to understand how to apply this Ampere circuital loop. But I'll suggest you people first note down this law, at least you get familiar with the statement, then we'll start with cylindrical wire. Cylindrical wires question has come a lot, I'll tell you. 2016 also in your CBSE foreign papers and all these. This has come. No need to write this from here only. Asta, when is your half yearly exam? What was the date that you mentioned?
Yes, ma'am.
You were telling about your exam, no? So when is your exam, physics exam? What was the date you mentioned to me?
20 September.
20. Okay.
Ma'am,
Yes. Who is this? Anushka. Yes.
ma'am, our half-yearly exam will be starting from 10th October. So how will be the classes be taken then?
Your exams are from 10th October. And what's the syllabus, Anushka, for you?
Ma'am, we are not shared with the syllabus and the timetable yet. The school will
Okay,
provide.
right now you have no information. All right. So before your vacation, what was the chapter that ended?
Ma'am, we were just done with the fourth chapter. Now we've started the fifth.
Okay. So I think most of it is EMI or AC. I think it should come. Fine. Let me know whenever you get the syllabus. So Anushka, that time what will happen? See, these classes will be going on, but according to your exam, the way I was asking Astha's her exam because she's having some chapters extra which won't be completed by that time. So we can have certain extra classes, and other students also from other batches are also having their exams. So for exams, you can be prepared also, but obviously for the exams and the type of classes that will occur, that will be a slightly they will be different. The classes that you have in on regular basis, those are in much more detail. Fine, Anushka.
Yes,
So whenever your exams are beginning, whatever is the syllabus, whatever is the schedule, you can inform me. According to that, we can plan.
yes, ma'am.
See, let's start with the steps. All of you must have written this. So cylindrical wire we are doing, but from here you can see the steps. See, what just a name given that steps. Ultimately, you know what we have to do. Choose an Amperian loop. Right now for the circular wire, we have chosen an Amperian loop that is just in the form of circle whose radius is smaller. Fine. So step 1 is choose Amperian loop. Usually you have cylindrical wire only given. Maximum time in your exams also. Cylindrical wire case is only given. Otherwise, it will be a simple case. And if something else is given, then be prepared. Second step includes application of Ampere Circuit Law. Ampere Circuital Law was what? Ampere Circuital Law is your P dot dl. This is equal to mu naught I. Fine. Now step 3. Step 3 will be what? B will be kept over here. Integral of dl mu naught I. Integral of dl will be 2 pi small r mu naught I. Magnetic fields formula for a cylindrical wire is mu naught I divided by 2 pi r. Now this is not enough because you can be given cases, different cases. That cases question I have written below, but just note this down quickly, then we'll do that question. That is an important question, very important, more important than this. Just note these down, these points quickly, then we'll do that. Cylindrical wires, 2 cases.
One minute, man. Can you just scroll up? Just step on all those steps. Okay, done now.
No, Shriyansh, for especially JEE mains, there are, as I've I think mentioned you before also, apart from this, these are 2 classes that you have per week. So there will be one more additional class for JEE mains, for NEET as well, whichever subject you want. That will be one additional class. If you wish, you can get the information about that. So all the CBSE or that derivation part will not be done there. Just it will be focusing on your JEE mains. All right, Shriyansh.
All right, ma'am.
So it will be like 3 classes, 2 classes with me and 1 additional classes that will be just focusing on your JEE exams. The previous exams, previous year's question from JEE and all, these are included. So these are 3 classes. So 2 teachers will be teaching. I'll be teaching you on the weekends and 1 more class, whichever batch that you would prefer, that will be kept on the 3rd day. Done. Yeah, I'll show you the question and answer you can write all along. I'll do this question. It says calculate the magnetic field. Now see, what's the question? Question is mainly cylindrical wire we have seen. There are two cases possible, and please mark this question important. Even in the half-yearly exams also, schools do give this question. Now see, there are two regions for a cylindrical wire. Let's say, let me draw a very broad diametered cylindrical wire. First case there. First case is inside. This is the same wire, the thin wire that we draw. I'm just drawing it broad because we have to move into and see into the details of it. So radius is A. Fine, radius of this is A. And the whole current that is flowing through this wire is I. I current is flowing through this wire. Again telling you this, I have drawn it broadly, otherwise it's just a simple wire like this. It's a cylindrical wire like this. Now first part says, calculate the magnetic field within a region inside whose means Ampere Circuital Law's radius, the Amperian loop's radius is small r. Radius of cylinder is A. Fine. A is the radius of cylinder, small r is the radius of Amperian loop. Got it? Now R is lesser than A. That is your first part. It means if your Amperian loop, this is a circle, this will be the Amperian loop whose radius is small r and small r is less than. Now, first part, first step, drawing the Amperian loop is done. Second step involved writing the formula for it. B dot dl is equal to mu naught I. Now, I is what? I enclosed is over here. Before we focus on to see, B dot dl part is easy. B dot dl portion is easier. We'll do it. Regarding I enclosed, see, I was the current flowing through the entire cylinder, through the entire cylindrical wire. We are just focusing right now. We want to find the current through this region. There are certain extra current present in our Amperian loop. We want to find out the enclosed current. And current enclosed where? Enclosed within the loop. So within the loop, you do not have I current. I current is for the complete wire. For this specific region, we want to find out. So it means I enclosed will not be I. Clear? Any doubts in this step? Why are we not writing I enclosed as I? Because I is for the entire wire. We are just choosing for a narrower section. That's why I enclosed is not I. So what will then be I? See, you will do it in this manner, that pi a square area has current equal to I. Agreed? Pi r square has current I. So unit area will be what? 1 unit area. Just apply unitary method. It will be I divided by pi a square. This is for 1 unit area. And for which area do we want the current? For pi r square we want the current. So for pi r square area, it will be I by pi a square for 1 unit multiplied for the entire unit, that is pi r square. Got it? Pi a square has I current. Unit area has I divided by pi a square. So if you know anything for unit, just multiply it by any other quantity which you want to calculate. So pi r square will be having I multiplied by this. So I enclosed, this will be equal to I r square divided by a square. This is the difference just that will come, and the examiner wants to see this pattern. That's why this question is very famous for me. Now applied, B integral of dl will be mu naught. I enclosed will be I r square divided by a square. dl integral will again be 2 pi r. This will be equal to mu naught I r square divided by a square. This r, this square will divide each other and cancel off. Magnitude of magnetic field. This will be what? Mu naught IR divided by 2 pi A square. Fine, this is the formula that we obtain. It is a hollow cylindrical wire, yes. See, no, this is a solid cylindrical wire. If hollow cylindrical wire is mentioned, then you have two radius. Hollow will be having two radius. The above part, no, it will be concentric like this. So outer radius will be there, inner radius will be there, then there will be a radius of the empyrean. This is a solid, and by default in your exams, whether it's a sphere, whether it's a cylinder, by default, if nothing is mentioned, use it and choose it as solid. Hollows are special cases which will be given to you. But certain cases there are different, like electric field, you must have seen an application of Gauss theorem. So those are different. So concentric will be there for hollow. Solid is a complete single wire. So that's why we are not taking two radius. One single radius for a solid one and one for the empyrean. This is the formula that we get. A is what? A is the radius of cylinder and R is the empyrean loop's radius. Second part says what? Second part says region outside. Now second part is easy. In this part also, just this fact was important, how you choose I enclosed. So whenever in exam you're solving this question, be alert. You have to mention I enclosed. Examiner sees this and the rest of the things are definitely okay. This was the wire. Now a point outside. That's why I've drawn the wire narrower. This is point A. Now the empyrean loop is greater. This is your empyrean loop this time with radius smaller. Fine. This time what has happened? R is greater than A. This is a region outside. One more thing you can do, class, is that you can remember these formulas also. Fine, you can remember these formulas. Especially for your entrances point of view, these formulas are important. It will be given to your cylindrical wire has the value of radius as this and this. Everything will be given, calculate the magnetic field. So it's better if you remember. And derivation, you have to remember at any cost because this will be asked. It's actually a kind of derivation only, cases for cylindrical wire. It's just that we are doing it in the form of question. Because in the exam, in your previous papers, it has come a lot in the form of question. Now see here, this part becomes very easy because this time I enclosed will be what? Can anyone answer this? What will be I enclosed this time? Anyone? For this pi r square. See, now your empyrean loop is enclosing the complete wire like this. The complete wire is enclosing. So I enclosed will be what? Total current I encloses total current enclosed within the loop. So here the total current enclosed within the loop is I only. That time what happened? We were having certain extra current. We wanted a part of that I. Right now, in this part, we are not finding a part of I. Whole I is enclosed wire. So I enclosed this time will be I only. And now derivation will be what? This will be B dl is equal to mu naught I. This part we have already done when we were discussing that. 2 pi r mu naught divided mu naught I, and magnetic field from here is mu naught I divided by 2 pi. Got it, class? These are the two cases. So it is independent of the radius. Now one thing. One more thing can be asked. Maximum this can be asked. If beyond this, nothing will be asked. See, this is your magnetic field. This is your empyrean radius. Please, class, pay attention to this graph. This is the center. R is equal to 0 means center. Let's say R is equal to capital R. When your empyrean loop's radius and the cylindrical wire's radius is equal, it means they are overlapping or it's the surface. So R is equal to capital R is the surface. Fine. I'm just marking certain points on the x-axis. So r is equal to 0 is at the center. R is equal to r is at the surface. Fine. So between the surface and the center, between the center and the surface, any part will be inside, right class? If you have a circle, if you have a wire, cylindrical wire also, from the center to the surface, whatever point you choose, that will lie within. So from the center to the surface, this will be less than r and it will be inside. And contrary to this, if your r becomes greater, then this point is outside. This is how we have marked points. Now C class. From 0 to r means from the center to surface, that is inside. Inside, I think we had done in the first part. How did B and R vary? Look into the formula. How are magnetic field and small r varying with each other? Directly proportional, inversely proportional, independent, what class?
Directly proportional.
Directly proportional. Good, Asta. They are directly proportional to each other. So the type of graph that you obtain, this will be a straight line. This will be a straight line because magnetic field is directly proportional. Till when? Till the surface. This part is inside. Agreed? Now the outside part we have seen. Both are inversely proportional to each other. So the graph will be a hyperbola. This will be the nature inversely proportional to R. This is inside, this is outside. So this graph can also be asked. Maximum to the extent that can be asked is this graph. Clear to all of you?
Yes, ma'am.
And what about you, Mariam, Priya, Darshini, Razan? Clear?
Yes, ma'am. Clear.
Yes, ma'am.
Yeah, but though I understood the thing, but how did we get the hyperbola again? Can you just explain?
Inversely proportional. See, when two quantities are inversely proportional, if your x is inversely proportional to y with a whatever power, y is inversely proportional to 1. If your y is inversely proportional to x, y is inversely proportional to x square, or y is inversely proportional to x cube, the nature of the graph that you obtain is a hyperbola. So that's why it is showing that it is inversely proportional.
Okay. Thank you.
So yes, quickly note it down. I think 4 to 5 minutes are only left.
Ma'am, can you just scroll up for a second? Done, ma'am.
Just text me done when all of you have written. And all those who have written, you people can start leaving already 4 minutes I think extra. I've taken today. Tomorrow we'll continue with solenoid and toroid. All right.
Ma'am,
Thank you, ma'am.
just
Bye,
one
ma'am.
thing.
Yes, yes, Iman.
Ma'am, how can I join the WhatsApp group? Because I haven't joined. So,
You are not added on the. I'll add you. I'll add you first, and I'll send you. Sure. Fine.
okay.
I'll get you added.
Okay.
And someone else also was saying something. No, Asta. Asta, were you asking something? Oh. Ma'am. Yes, Razan.
Ma'am, in the graph, what is the capital R?
In the where in the this graph,
Yes, ma'am.
capital R is the radius of the wire that I've taken. Because A was specifically restricted to that question we had taken. This graph is a generalized graph for cylindrical wire. So capital R is the radius. That's why when the radius and small r is ampere